When atoms absorb energy, it's actually the electrons that absorb the energy. These electrons get energized. When they absorb the energy, they jump to higher energy levels. And in order to jump to these higher energy levels, they need a minimum amount of energy to do this. If they don't absorb enough energy, if they don't absorb a large enough photon, they aren't going to change in energy levels. They'll just stay put where they are. Once those electrons are energized, they only stay a very short time in the higher energy level. When they're ready to leave, they jump back down to a lower energy level. Sometimes they go to the energy level where they started. Sometimes they fall to an energy level that is higher than where they started. And when they fall to this lower energy level, whatever it is, they give off energy, they give off photons. Depending on the amount of energy they give off when they fall back to their lower levels, they're going to generate visible light rays, or infrared light rays, or ultraviolet light rays in general. And those light rays that they emit are called spectra, emission spectra. Line spectra are the visible light colors that we can see when the electrons fall to lower energy levels and give off visible light rays. You can also have UV line spectra and infrared line spectra. They give off light of particular bands, or UV or infrared radiation at particular bands. So if it's a visible spectrum, they look like lines of color. They're discrete energy levels that the electrons give off, and so discrete bands of light, whether it's visible or infrared or ultraviolet, are what are produced. And these thin pattern of lines of light are called the line spectrum. It's also called a bright line spectrum sometimes, and it looks like this. Okay, this is a bright line spectrum for helium, and if you take a look at it, what you'll see is there's a band of red light at 668 nanometers, a band of yellow-orange light at 588 nanometers. We have some blue light and some violet light between 500 and 400 nanometers. So this is characteristic of helium. It's called the helium emission or bright line spectrum. It is produced from any helium from any source, whether it's in a chemistry lab or from the sun or from another star. Because each atom is constructed differently, has a different number of electrons, and those electrons have different amounts of energy, the spectrum that you see for each element is going to be different. So due to the nature of the atoms, their energies are going to be different, and so the wavelengths of bright lines produced by each element are going to be different. This is one way to chemically identify elements, is by identifying the bright line spectra of those elements. We can use this equation to figure out the relationship between the wavelengths of light produced and the amount of energy involved in the electron emission when it's dropping from high energy to low energy. So if we know the wavelength, Planck's constant is a constant, C is a constant, the energy is proportional inversely to the wavelength. It's proportional directly to the frequency, as the first two equations show us. So the energy that we find by using this equation is actually the energy per photon of light. Each electron absorbs a photon of light to jump to higher energies. Each electron gives off a photon of light when it falls to lower energies. One way that we can look at or describe this model is it is considered a stair step rather than a ramp model, since there are only discrete amounts of energies that can be absorbed or given off by electrons rather than a continuous range or spectrum of energies that can be given off or absorbed by electrons. Niels Bohr was prominent in his experimentation and contribution to our knowledge about how electrons behave, especially his work with the hydrogen atom. He described the hydrogen atom electrons as moving only in specific regions around the nucleus. He studied the hydrogen atom extensively, and what he found was those regions where the electron was found in the hydrogen atom were specific distances from the nucleus, and only specific or fixed distances from the nucleus. His studies contradicted what we've learned in classical physics. In classical physics, we have a particle that moves in a straight line, according to Newton, unless it's acted on by some sort of outside force. In this case, we have an electrostatic force between the positive nucleus and the negative electron. We also have a gravitational force between the massive nucleus and the lower mass electron. Both forces trying to pull the electron into the center of the atom, into the nucleus. So what that gives us essentially is a relatively circular path that the electron follows around the nucleus. Now what we also know from classical physics is that moving particles or accelerating particles give off energy. And if they give off energy and the electron's a moving particle, it should eventually collapse into the nucleus. But we know that that doesn't happen because atoms tend to be really stable. So why doesn't it fall into the nucleus? And what Bohr found out was, well, different things are going on at an atomic level than there are in classical physics. And so he and others working at that time in conjunction with him came up with the idea of something called quantum physics. And these quantum referring to bundles or packages. We talked about quanta. It's an amount of energy in a photon. So what they determined is electrons can't change position, meaning they can't move closer to the nucleus or further away from the nucleus by changing energy levels, unless it gains or loses a specific amount of energy, the correct amount of energy to take it to the next energy level. So it's very specific. It's similar to if you're walking up the stairs, you can't lift your foot 3/4 of the way up to the next step and expect to go up. You have to lift your foot a specific distance to get all the way up. Same is true for electrons moving from one energy level to another. And what Bohr created was an equation that helped to explain mathematically the bright line spectrum that he saw for hydrogen. And this is the equation that he created, E for energy. This is the energy of a photon, and each photon energizes or is produced by the motion of one electron. So he came up with this constant, 2.187 times 10 to the negative 18 joules. In the equation we've got Z and we have N. N is an integer, it's the energy level. When we get to quantum numbers, it's the principal quantum number. Z is the nuclear charge. Nuclear charge is the number of protons. When I completely remove an electron from the atom, so I turn it into a positive ion, the energy for that electron is 0 because N is infinity. The electron is infinitely far away from the nucleus. N is small, close to the nucleus. N is large, further from the nucleus. Ground state for an electron, ground state meaning the lowest energy level for an electron. In hydrogen, the ground state is N equals 1. Hydrogen only has one electron. It's going to want to be in its lowest energy state, so it's going to be in the energy level closest to the nucleus. We can calculate the amount of energy an electron gains or gives up as it moves from one energy level to another. If we look at an example where we have an electron going from N equals 1, or the energy level closest to the nucleus, all the way up to N equals 6, which is one of the higher energy levels, further from the nucleus, we're going to calculate that energy for each N value. So when N equals 6, we're going to put in our numbers. Remember, Z is the number of protons. Hydrogen has one proton. We're going to the 6th energy level, so we get a particular amount of energy for an electron at that energy level, negative 6.05 times 10 to the negative 20 joules. We're going to do the same thing for N equals 1, figure out how much energy an electron possesses there. And then if we want to find out how much energy is absorbed or given off when the electron makes this transition, we're going to take the difference between these two energies. Turns out the larger my negative number, the more stable the state. So in this case, this is larger. So an electron is much more likely to be in N equals 1, or the lowest energy level, rather than N equals 6. So it's going to want to stay in its ground state or more stable state. So again, as we move the electron from N equals 6 to N equals 1, it's going to give off energy. We're going to take the difference between those two energies, and we're going to find that it gives off 2.117 times 10 to the negative 18 joules, and that's its change in energy. So in emission spectra, the energy given off, the spectrum lines that we see, are due to the changes in energy. So we have a couple different diagrams that we can look at here. On the left, we have a vertical representation of energy levels. As energy goes up or increases, we're going up vertically in our diagram. Each of the lines represents a specific N or energy level. As the energy levels get further from the nucleus, they also get closer to each other relative to their distance. So the energy from 1 to 2 is a huge jump. Energy level from 2 to 3 is a smaller jump, and as we get higher in energy levels, they get closer together. So as an electron jumps from each energy level down to the lowest energy level, what we see is a variety of light waves given off. In this case, they're represented by blue, green, and red. If we look at a diagram of an atom, similar to what you might have drawn in middle school where it's circles. Energy level n equals 1 is closest to the nucleus. Energy levels larger than 1 work their way out. And so as an electron jumps from a higher energy level to a lower energy level, it gives off energy, and those becomes the lines we see in our bright line spectrum. We have wavelength of light of 93.8 nanometers. We have a change in energy equation where we're going from n equals some number to n equals some other number, and so we can try and figure out what is the energy change between these two. What produces this wavelength of light? So when that negative sign is there for delta E, energy is given off, so we are forming an emission spectrum. For emission spectra, we have three different kinds we can have. We have ultraviolet emission spectra, we have visible emission spectra, and we have infrared emission spectra. If my ending energy level, the level to which the electron is falling, is 1, and that it starts from is higher, 2, 3, 4, 5, 6, what I get is a series of lines in the ultraviolet spectrum. If my ending n is 2, so the electron is falling down to n equals 2 rather than n equals 1, it's called the Balmer series, and these are emission spectra in the visible light range. If it's falling to n equals 3, then I have what's called the Paschen series. So the electrons are falling to n equals 3 from higher energy levels, and what I get is the infrared emission spectrum. The Bohr model came up with all these equations, came up with all this theory, and used the theory to explain why they saw the hydrogen spectrum and why it existed the way it did. His model was great for hydrogen, wonderful for hydrogen. Problem is, it doesn't work very well for any other elements. All other elements have more than one electron, so it makes it more challenging to figure out how to deal with it.